Hello Academy, I am Sidhartha, I am your physics teacher. Okay, now in our last class we have discussed about what? In a chapter, second chapter, electric potential and capacitance. In electric potential and capacitance, we have discussed till what is the relationship between electric field and electric potential. We know electric field is equal to E is equal to minus dV by dr. Now another next topic is what? Equipotential surface. So equipotential surface, what is the meaning of equipotential surface? So equipotential surface is any kind of surface, each and every point its potential difference is same. Okay, then again I repeat, equipotential surface means in each and every point potential difference is same, is called equipotential surface. It is any kind of surface. Suppose one surface is there, suppose this is one kind of surface, suppose each and here lots of charges are accumulated here lots of charges are accumulated here. Okay, lots of charges are accumulated here. So these charges, each and here all the charges have potential difference is same. Here all the charges has same charges or potential difference is same in everywhere. So this type of surface is called equipotent surface. Now some properties in our exam we have known that the properties of equipotential surface. Next one is called properties of equipotential surfaces. Next one is called properties. So what is the main properties? So what is the properties of equipotential surface? So first of all, first property is what? First property, equipotential surface has a first property is what? No work is done. No work is done. No work is done in moving a take charge over an equipotential surface. What is the meaning of that? No work is done in moving a take charge over an equipotential surface. Suppose this is one kind of equipotential surface. Here the charges are there. So these are charges. Suppose this is Q1 charge, this is Q2 charge, this is Q3 charge, this is Q4. Suppose this is Q5 the charge. Suppose another one charge. So this is Q0 charge. This is called take charge. Suppose if you move the take charge from any point, this work done will be zero. Why? Each and every point potential difference is zero. No work is done in equipotential. No work is done means work done is zero. Means work done is zero means what? Suppose we know the potential difference. Suppose here the potential difference is 1. Here the potential difference suppose VA here is V1. Suppose here another, we have discussed another way. Suppose this is a surface. So there are suppose these are potential. Suppose Q1 charge. So these are the Q2 charge. This is Q3 charge, and this is suppose Q4 charge. Suppose another charge, suppose Q0 charge. So here the potential difference suppose V1, and here potential difference suppose V4. What is the potential difference between this one? V4 minus V1. No work done is V1. We know V is equal to W by Q0. Q0 is a take charge. This is a take charge. So V4 minus V1 is equal to what? No work is done in the equipotential surface. Means no work is done means what? So work done will be zero means what? Work done will be Q0 is equal to 0. So V4 minus V1 is equal to 0. So V4 is equal to V1. That's why V4 is equal to V1 means what? Each and every point equipotential surface, each and every point potential difference is same. This is called equipotential surface. Okay. So first property is satisfied that no work is done in moving a take charge over an equipotential surface. Okay. Work done is zero. No work is done. Work done is zero. Work done, it cannot be done the work. Okay. So after that, so next 2 point is what? Electric field. Next one is called electric field. Electric field is always normal to the equipotential surface at equipotent surface at every point. Electric field is always normal to the equipotent at every point. Suppose each and every, this is an equipotential surface, this is an equipotential surface, each and every point equipotent surface normal means 90 degree. Normally they can erect to say, normally they can erect, normal means perpendicular to the surface. So this is always normal. Okay, this is one another point. Okay, so next one, third one is what? Equipotential surface are closer together in the region of strong field and further apart in the region of weak field. So this is the main another point is what? Equipotential surfaces are closer together in the region of strong field and a further apart in the region of weaker field. Means equipotential surfaces are, suppose two equipotential surfaces are strong equipotential surface, they can closer. If they can attract each other, they can closer itself. And if the two weak are, they can further apart. So this is the meaning of that. Next fourth point is what? No to equipotential surface, no to equipotential surface cannot intersect each other. No to equipotential surface can intersect each other. No two equipotential surface can intersect each other. Means what is the meaning of that? Suppose two equipotential surfaces are there, they cannot cross each other. Why? If they cross, the two values are not possible. If they cross, it's a point of intersection, two values which is not possible. So next another one topic is called electrostatic potential energy. Electrostatic potential energy of a two-point source system of potential of a system electrostatic potential energy of a system of two-point charges of two-point charges. So how can you represent electrostatic potential energy of a system in a two-point charge system? So how can we explain this electrostatic potential energy of a two-point charge system? Suppose we know that electrostatic potential energy means what is electric potential? It is the amount of work done to bringing a unit positive charge from infinity to that point is called electric potential. So electric potential energy is called one kind of work done. Suppose if we want to carry a charge from infinity or anything or one point to another point, this work done will happen. So this work done we can consider as a electrostatic potential energy against this charge. Suppose we can consider, suppose here one point, suppose P1, and this P1 point we can present a charge Q1. So another charge, another point P2 we can consider, and this is called, distance is called suppose R12. Okay, so now in this case, first of all, in this case, work done will be what? If there is no work done bringing first charge, if we bringing a charge Q1 in the particular point P1 due to Q2, work done will be what? First work done will be what? 0. Now, now electrostatic potential energy Q1 at point P2. So what is the point P2? What is the electric potential energy here? So electric potential energy, electric potential at point P2 will be what? At point P2 will be what? V1, we can call electric potential energy 1 by 4 pi epsilon naught Q1 by R12. But we know that V is equal to what? 1 by 4 pi epsilon naught Q by R. So this is the electric potential energy formula. So suppose at a particular point Q1 point here, this point P1 point, we can place a charge suppose Q1. So here the distance is another point P2, we can place another point, we can give it one point, this is point P2, here this distance is R12. Okay, now whenever I bring a one positive charge Q1 from that P1 point, then what is the amount of work done here? Work done 0, because there is no work done between the two charges. If one charge, another, the source charge is there and another one charge is from the infinity, then work done will happen. But if we bringing or moving a single charge, there is no work done. Okay, so that's why work done will be 0. So another one, electric potential at particular point P2, what is the work done? V1 is equal to 1 by 4 pi epsilon Q1 by R12. So another charge, suppose infinity, if we bring another charge Q2 here from infinity, so what is the work done here? What is the work done? So work done is equal to what? Work done in moving a charge Q2 at a distance R2 distance R12 from P1. Then what is the work done here? We know that V is equal to W by Q naught or Q. W is equal to what? V into Q. So here we can call as W2, work done W2. Already W1 work done is 0. So W2 will be what? W2 will be what? Potential into charge. Okay. Charge. Potential means what? What is the potential? What is the potential here? V1 and charge what? Q2. So W2 is equal to what? V1 means 1 by 4 pi epsilon naught Q1 by R12 into Q2. So work done will be what? The work done will be what? 1 by 4 pi epsilon naught Q1 Q2 by R12. This is work done total. So then and total work done will be what? Next is called total work done. W is equal to what? W1 plus W2. So W1 is equal to 0. W2 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. So we are getting what? W is equal to what? 1 by 4 pi epsilon naught Q1 Q2 by R12. This is the amount of work done to bringing the two charges. So this work done we can store as a what? Electric potential energy. This work done we can consider electric potential energy. So this work done is stored as a stored as a potential energy. So U we can call as U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. So this is the electrostatic potential energy of a 2-point charge system. Again I will repeat this one. First of all, suppose this is a point P1. Another charge we can bring here and Q1 at point P1. And another point P2 here, this is a point P2 and this is R12 distance. So what is the work done to bringing from here to that point? The work done will be 0. So there is one charge, we can bring in one charge in from infinity to that one, this we can work done 0. So now electric potential at the point P2 will how much? From that to that, what is this is a charge here Q1, and from that one the electric potential is how much? P1 is 1 by 4 by Q1 by R2. And again another charge from the infinity you can place at the point P2. Work done in moving a charge from Q2 to how much? Work done will be what? Potential into charge. Which potential? This is V1. So charge how much? This is Q2 charge. So 1 by 4 pi epsilon Q1 by R2 into Q2. After that, this is the work done number 2. So total work done is how much? W1 plus W2. Work done is equal to what? W1 plus W2. Then W1 is equal to what? 0 and W2 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12, and this work done will correspond to the potential energy. So this is the potential energy of a system of 2-point charges. Okay, this is very important. Next point. System of 3-point charges. 3-point charges. Potential energy of 3 points. Earlier, same diagram where again this is P1, this is Q1 charge, this is P2 infinity pura. So this is Q2 charge. Distance is how much? R12. Another third number charge we are placing at the point P2. This charge is suppose Q3. So from here to here, the distance will be what? R13. From here to here, distance is R23. From here infinity, this is another infinity. To find it, first one, W1 is equal to 0. W2 is equal to how much? 1 by 4 pi epsilon naught Q1 Q2 by R12. Another W2 is W3. How we can calculate it? W3 is equal to what? Potential into charge. Potential into charge. So what is the potential? Potential from this point to this point plus this point to this point. So potential from this point to this point how much? 1 by 4 pi epsilon naught Q1 Q3 by Q1 by 1 by 4 pi epsilon naught Q1 by R13 plus 1 by 4 pi epsilon naught Q2 by R23. This is the total potential, and charge will be what? This charge is Q3. Okay. Suppose here the charge will be from here, same diagram, but another one is suppose these two point charges we have already done this work done. Okay, this work done is also started as a potential energy. Thus another charge will place it here, this point Q3 at point P3 point suppose. This is P2 point. Okay. If we place another charge for infinity, then from that point to that point, what potential difference is created, and here that point we can calculate the potential difference. So we know W3 work done will be what? Potential into charge. This which potential? This potential plus this potential. So 1 by 4 pi is Q1 or Q1 by R13 plus 1 by 4 pi epsilon naught Q2 by R3 to Q3 to 3. So after that, after multiplication, what? 1 by 4 pi epsilon naught Q1 Q3 by R13 plus 1 by 4 pi epsilon naught Q2 Q3 by R23. So this is this much of work done. So this much of work done W3. This is the work done W3. Now total work done is how much? Now total work done W is equal to W1 plus W2 plus W3. W1 will be 0. W2 will be 1 by 4 pi epsilon naught Q1 Q2 by R12, and W3 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R13 plus 1 by 4 pi epsilon naught Q2 Q3 by R23. Now what is the formula for 1 by 4 pi epsilon? We can common here. So what is the Q1 Q2 by R12 plus Q1 Q2 by R12 Q1 Q3, sorry, this is Q1 Q3 by R13 plus Q2 Q3 by R23. This much of work done. This is a total work done. This work done is also stored as potential energy. So potential energy we can represent as 1 by 4 pi epsilon naught what? Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. So this is the potential energy. This is the potential of a 3-point charge system. Is it clear to everyone? This is the potential energy of a 3-point charge system. Okay. So now units of electricity potential energy. So unit of electrostatic unit of potential, U is equal to what? We know U is equal to Q into del V. This is a formula because Q into volt. So Q is equal to what? One charge we can consider, you can 1.6 into 10 to the power minus 19 coulomb, because Q is equal to one charge. So one charge, either it may be electron or proton. So charge will be what? What is the value of one charge? 1.6 into 10 to the power minus 19 coulomb. So 1.6 into 10 to the power minus 19 coulomb. So we know this formula is equal to how we can came from this formula. We are already discussed that work done for 2-point charge system, 3-point charge system. This work done is also stored as a potential energy. This potential energy is equal to what? What U means what? How we can convert it? That V is equal to what? W by Q naught. Q naught. So W is equal to what? V into Q means potential difference into potential, electric potential is the charge, or charge into, we can call as Q into V. Q into V also. This work done is how we can also the potential energy Q into V. So Q into, that's why this work done is also stored as a potential energy. So U is equal to Q into del V. So here Q is equal to what? 1.6 into 10 to the minus 19 coulomb. So either it may be one electron or another proton. So this value is always constant. So this constant is called 1.6 into 10 to the minus 19 coulomb. So another one, del V means small amount of voltage we can call as 1 volt. So now place this one, 1.6 into 10 to the power minus 19 coulomb into 1 volt. So after that what? How 1.6 into 10 to the power minus 19 coulomb volt is called what? 1.6 into 10 to the power minus 19 joule. And this one is 1.6 into the minus 19 joule we can call 1 electron volt. So this is called, so SI unit of electrostatic potential energy is called electron volt. So 1 electron volt is equal to what? 1.6 into 10 to the power minus 19 joule. So this is the about, okay, unit of electric potential energy. Okay, this is all about the electric potential energy. Okay, so in this way 1 milli electron volt, we know 1 milli electron volt is equal to 10 to the power minus 3 electron volt. 1 mega electron volt, in this way you can calculate mega electron volt means 10 to the power 6 electron volt. 1 kilo electron volt is equal to what? 10 to the power 3 electron volt. 1 giga electron volt is equal to what? 10 to the power, giga means 10 to the power 9 electron volt. 1 tetra electron volt, in this way we can calculate 1 10 to the power 12 electron volt. So these are some bigger and smaller unit of electrostatic potential energy. Okay, so another one important topic is what? Another one important topic, potential energy of a dipole in a uniform electric field. Potential energy of a dipole in a uniform electric field. So in a uniform electric, potential energy we have already discussed. So in a dipole, suppose uniform electric field. So this is called as uniform electric field. This is called as uniform electric field. We are placing dipole here, one dipole. So dipole here. This is minus q charge and this is plus q charge. So this is the twice a distance here. Okay. So it is a uniform electric field. This charge plus q and this is minus q. If we place a charge in an electric field, what will happen? If we place an electron or proton in an electric field, the force will develop. So what is the amount of force here? So amount of force, we know that E is equal to F by Q naught, or F is equal to what? Q naught E. So force is generated in this direction is equal to what? Plus QE. And in that position, another force is generated. This is called minus QE. One plus QE and minus QE. So here force will be in this direction and another one force will be in that direction. What will happen? The dipole is rotated. If dipole is rotated, what will happen? Dipole is rotated means what? Torque will produce. In our last class 11, torque, how we can consider a torque? Torque is a one kind of moment of force. Newton meter, unit is Newton meter. Torque, how we can convert it in torque? Torque means what? Either force into perpendicular distance. So here we can call as what? Torque is produced. Torque is produced means what? One kind of one moment of force will produce. So torque means is rotated, so torque will produce. So another one, we have perpendicular here. we can perpendicular what? Here theta will be considered. So we know that sin theta is equal to what? Perpendicular by hypotenuse. So perpendicular is equal to what? H sin theta. So H is equal to, we can consider it twice. This we can consider hypotenuse twice. The twice sin theta. So this perpendicular distance is equal to twice sin theta. Okay. So if it's now torque will be what? Torque is called tau, acting on the dipole. On the dipole will be what? Tau is equal to what? Force into perpendicular distance. This is a formula. So force means we can take any force. We can call suppose QE into perpendicular distance how much? Twice a sin theta. So tau is equal to Q into twice a means how much? P dipole moment. So P sin theta. We are getting what? P sin theta is a torque acting it here. P sin theta is equal to torque acting on this dipole. If you rotated this one, what is the dipole is created? This dipole is equal to what? P sin theta. So if P sin theta, we are assuming that, but our aim is to calculate what? Potential energy of a dipole in a uniform electric field. Our aim is to calculate what? Potential energy, but not that torque. So how we can calculate a potential energy? But in our last this discussion, we are discussing what is potential energy. If we done work done will be from infinity to that point, work done will be there. This work done is stored as a potential energy. Now we can calculate the work done. So now work done will be what? So work done will be what? We know work done is equal to what? Force into displacement. So dW work done is equal to what? dW work done is equal to what? What is the dW work done in this case? If it is rotated, what is the work done will happen? Work done is rotated, which force is responsible for this? This is torque. What is rotation? Theta. So tau d theta is the what? Work done here. So it is tau d theta. The total work done will be what? Total work done will be W is equal to, we can integrate the dW. If it is integral theta 1 to theta, we can limit this one theta 1 to theta 2. So integration theta 1 or theta 2, then dW means what? Tau d theta. So now after that tau d theta. So after tau d theta, after that, to integration theta 1 to theta 2, tau means what? PE sin theta d theta. Okay, then P sin theta d theta, we are doing these things. So if you go for that one, that side, so total work done will be, so here theta 1 to theta 2 means what? P is the constant. So PE integration theta 1 to theta 2 sin theta d theta. So integration of sin theta means what? Minus cos theta. So PE is equal to minus cos theta, theta 1 to theta 2. We can place it here. PE what? Minus cos theta 2 minus minus plus cos theta 1. So after that PE cos theta 1 minus cos of theta 2. So this is amount of work done will be. This work done also is stored as a potential energy. Now we can write this equation in new form, that P is equal to what? Cos theta 1 minus cos theta 2. So this is amount of potential energy when we place a dipole in an electric field. Okay, this is another topic. In our next class we have discussed about capacitance of a conductor. Thank you.